So in this episode, we're going to start looking at how we model magnetic fields. It's very similar to how we modeled vector fields. We're going to start again with a potential. This A here is something we call the magnetic vector potential. It serves much the same purpose that the electric potential did, except that this is a vector potential. It's a vector quantity instead of a scalar potential, a scalar quantity. It's created by the current density J here. Just like we had a charge density before, this is now the current density. You can think of this as how much current you have passing through a certain cross-sectional area at any given moment. Or it might be set by boundary conditions. Just like we had before, A is going to have a set of boundary conditions. So we're again going to imagine that we've got a square region. We've got a square region somewhere in here, and we want to divide this into a grid. So we're going to imagine making little tick marks along the x-axis, tick marks along the y-axis. And so just like we did for electric fields, the x-coordinate is going to be replaced by xi. So this would be I equals 0, I equals 1, I equals 2, I equals 3, all the way up to however many slices we have along the edge of the grid. Same thing with y. Y is going to get replaced by yj. It has to have a different index than x because these are independent variables from each other. And so we want to preserve that independence by giving them separate indices. So if you've got any point on here, instead of thinking of it as x comma y, we can think of it as I comma j. It'll be this point somewhere on that grid. So then we can replace A here. This vector A becomes A ij. Same thing with the current density j. This becomes capital J subscript I subscript j. And of course, these are vector quantities, so they have x, y, and z components. So you can think of this as really being a 3-index thing. You can think of it as being A at point ij with the kth component. So if you let k equal to 1, 2, 3, signify your component, then when we code this up, it can just be a 3-index thing that has 2 position indices and 1 component index. Same thing with the current density. I can think of this as j, I, j, k, and again, the k index just tells me what component I'm using. So we can use this recipe to transform this differential equation into a difference equation. So we have our Laplacian. We've seen how to transform that before. We'll have A to the right plus A to the left plus A above plus A below, all divided by our step size in x squared. And also up here we need to have minus 4 times aij. The reason there's 4 factors of this is because we're subtracting it from 4 neighbors around here. If we were working in 3 dimensions, we would have 6 up here, and this would be a 6 in front of the aij there. That's all going to equal negative mu naught. We'll just take mu naught to be 1 just for convenience for our code, equals negative mu naught j ij. And the solution process is really similar to what we've seen before. I'm looking to solve for this aij here. And so I'm going to put a dx squared over on this side. So I'll have on this side a dx squared times a negative jij. I'm going to move all 4 of these things over to this side. So I'll have an ai plus 1 j. I'll have an ai minus 1 j. I'll have my aij plus 1 and my aij minus 1. That whole thing is being subtracted over, so I need a minus sign in front of it. I'm left with this negative 4 aij. Everybody has a minus sign, so I can just get rid of the minus sign there. And the only thing left here is a 4, so my A at any point, right? Think of this as being at a central point that you're looking at, is going to be equal to the average of all the other points around it, right? So this is A to the right, A to the left, A above, A below. Added together, divided by 4 makes an average. So I've literally just got the average of all the points around it. A to the right plus A to the left plus A above plus A below plus dx squared over 4 jij. And so we're going to treat this the same way we did the electric potential. We're going to start with a guess for aij. We'll make it a decent guess. It'll at least satisfy the boundary conditions. We're going to feed that guess into the average calculation here, add it to this current density piece, right? This is going to stay the same because we know what this is. We're going to use that to get a better guess for aij. We feed those values into here because we're going to do this at every single point. All the points that were neighboring the one we were looking at before, they all get a better guess as well. We feed that better guess back into here. We feed that better guess into here, and we keep feeding it around until the thing converges. So the first thing we'll do is define the current density function that we're working with. This is that current density J. We are going to start out with 0 current density. We'll just be playing around with the boundary conditions in this episode. And then next episode, we'll take a look at the what this does. So this is just going to be a vector 0, 0 at first. The boundary conditions we'll define down here. So for example, you can think of the grid here. And so along the top edge, we're pointing to the right and up. Along the bottom edge, we're pointing left and down. Along the left edge, we're going to be pointing up. And along the right edge, we're going to be pointing up as well. And so everything else in the middle has to interpolate between those 4 extremes, but those are our 4 boundary conditions. The rest of it proceeds very similar to what you've seen before. We've got our setup of our x coordinates and y coordinates. That does not change. Here we create our a, but you notice this is a little bit different because it needs to have 3 indices. So we have the 2 indices for where we are in the grid. That's I and j, like we've had before for the scalar electric potential. Here we have a third index with 2 options. This is that index k that's going to determine whether we are talking about the x component of A or the y component of A. So even though k, I, and j are going to be appearing all together, it's I and j that kind of group together in your mind as the position along the grid. And then k is which component of the magnetic vector potential we are looking at. So that's the only piece we add there. When it comes to setting up our boundary conditions, again, we set up our A along the left edge, the right edge, the bottom edge, and the top edge, but we have to do it twice now. We have to do this once for the x component and once for the y components. Here's the x component, and here's the y component that we set up above. We'll play around with this a little bit more, make those a little bit more interesting, not necessarily uniform in a little bit. And then here what we've got is our target accuracy. It's going to be scaled by the problem. Let's see, we've set those to be 1 up here, so that'll end up picking up those 1s there, so that'll work out fine for us this time. And then here is our difference equation loop. This is really the only physics part. Everything else is just bookkeeping. We loop over I and j like we've done before, so we're looping over all the points. We also now have to loop over k so that we're getting the x component and the y component for A. Here we set up our difference equation. So here we've got that average value that we always have that shows you the point to the right, the point to the left, the point above, the point below. And we just have the extra index k to indicate whether we're talking about the x component or the y component. If you like, you can really think of this as being 2 functions, a function for the x component and a function for the y component, because those 2 pieces of information don't mix, right? We're really treating the x and the y components separately. So it's like you're doing a finite differences approach for 2 different functions, right? And then over here we do the same thing for j, calling out j as a function of x and y. And then of course we're getting the kth component of that output from J. But again, that's going to be 0 for right now, so we're not too worried about it right now. Then here we calculate the maximum difference between the old values and the new values. When we run this, it will get us out our A value, so our magnetic vector potential there. And then we come over here and we're ready to graph the thing. So we're going to graph this using these arrows like we did for the electric field previously. We've got to come up with our scale factors to worry about there. And then down here, we're just setting up each of our arrows. So we're going to create an arrow at each one of these points that we designate. And here is what we get. Here we have our up and to the right, our up and to the left, and then straight up, straight up. And you can see the magnetic vector potential fills in the gaps in between there. So we end up with these mostly pointing up here, mostly pointing up here, and in the middle, they kind of swoosh around a little bit. And then, of course, the magnitude is also dying off as you get closer to the center because it's getting farther away from those boundary conditions. So it's going back down towards 0 in terms of magnitude. Of course, we can make changes to those boundary conditions. Let's suppose instead of having the sides point up, let's suppose we had them point down. That's going to be a significant change because both the top and the bottom, the y component is positive. Here now the y component is negative. All right, awesome. We've got our new set of data. Let's see what this does to our graph here. Okay, so things are all kinds of turned around here. We've still got these pointing up, but now along the left and right edges, we have these going down. And so we get this really interesting swirling pattern in here. You can see that's going to be really useful when we talk about the magnetic field because magnetic field is based on the curl of this thing. So the curlier this is, the better a magnetic field we'll get to see. Let's try one other configuration. Why don't we try making this top part change a little bit? So let's see. So along the top edge, let's see, which one is the top? The top is A, K, I, M. So we'll do this for I in range 0 to m plus 1, A of 0, comma, I, comma, M. That's going to get us along the top edge. Let's have its x component, let's have it go like the sign of wherever we are. So we'll have x list of I there. I will need to import the sine function, I think, from NumPy. Let's go ahead and get sine and cosine while we're at it. And then we'll have the y component. So that's changing the x component. We also want to change the y component. So that's A1IM. We'll change that one to the cosine because we are moving along the x direction. We're changing I, so I want to be accessing the x variable. If I access y, y is a constant. It's not going to be that interesting. All right, let's try it with this new boundary condition. And now let's get our graph of here. Okay, and so now we've got quite a bit changing up along the top edge. So the vectors at the top are kind of turning around. I feel like I'm missing some up here. I suspect they're getting hidden by the top bar there. But you notice what's happening inside the field is we've got this top row here that's turning around. The rest is trying to turn around, but it's kind of getting beaten out by this one that is glued down. So the farther down you go, the less this is rotating around and the closer it is to this uniform pattern here, which is pretty cool.